All right, so it's my pleasure to introduce Aaron Roth. He's the 1940 Bicentennial Term Associate Professor of Computer and Information Science at the University of Pennsylvania, and he's co-director of the program in Network and Social Systems Engineering at UPenn. And he's really been a leader in the area of differential privacy. And so I invited him here today to give us a talk, just a kind of a survey talk, quasi-tutorial, I guess, as it were, about differential privacy. And so I'm really happy to have him do that. He's received the P. Award, as well as an Alfred P. Sloan Research Fellowship and an NSF Career Award, Google Faculty Research Award, and a Yahoo Academic Career Enhancement Award. And so without further ado, let me give him the floor, and please help me welcome Aaron Roth.
All right. Thank you for the kind introduction, and thanks for having me here at HoTSoS. I've long been a fan. It's nice to finally be able to participate. So, probably for this crowd, I don't need to sort of belabor the point too much that protecting privacy is important, but in case anyone is unconvinced, let me briefly make a case for it by going through a couple of well-known examples of privacy breaches. Okay, let me make the important distinction between privacy and security. In the three examples I'm going to talk about, it is not the case that, a hacker broke into some system or that any information that was not supposed to be released was released. Okay, instead, in these three examples, someone intentionally released some data set, thinking that it was innocuous, but it turned out that information from that data set could be used in unexpected ways to learn information about individuals. Okay, so in the first and maybe sort of silliest example, way back in 2006, AOL actually did a really nice thing. They decided to release to the research community a data set of search logs. Okay, AOL turned out had a search engine, and a search log data set is actually a really valuable and difficult thing to get your hands on as an academic researcher. It seems like you need to work for one of the big search companies, and so AOL thought, okay, we're gonna release this to the world. Now they were sort of aware of privacy concerns, and so they didn't have everyone's search history attached to their name. They redacted the names and replaced those with sort of numeric identifiers. But of course, removing people's names doesn't protect their identities when you have access to, like transcripts of their search logs. The New York Times, of course, noticed this. They interviewed Thelma Arnold, who was a person that they identified from this data set. She was, not happy about being identified. There was a class action lawsuit accusing AOL of violating the Electronic Communications Privacy Act. It sought $5,000 in damages per user of AOL search. One can only imagine that that's at least a six-figure sum. And AOL's director of research was fired. Okay. So the problem here was sort of pretty obvious, right? Like, they were releasing, people's search logs in the clear, removing people's names, doesn't do anything to protect their identities when you've got so much information. Okay, but similar things can happen with sort of less obvious releases of information. Who here is familiar with the Netflix prize? So for those who are not, Netflix decided, also in 2006, that rather than hiring lots of software engineers who are expensive to improve their recommendation engine, they were going to hold a contest. Okay, they were going to offer $1 million for the first person who could improve the performance of their recommendation engine by 10% or more. Okay, but in order to hold a contest, you need to provide data to people. Okay, and so they released a supposedly anonymized data set of movie rental records. Okay, so this is a big matrix where the rows correspond to people, the columns correspond to movies, and the entries are just a couple of pieces of information. Did you watch the movie and when, and how did you rate it on a scale from 1 to 5? Okay, and similar to AOL, they didn't release people's names. They replaced names with unique identifiers, numeric identifiers. This somehow doesn't seem so bad, because you don't have sort of the same, volume of information you have for search logs. Okay, but nevertheless, it turns out it's possible to re-identify this kind of information. Arvind Narayanan and Vitaly Shmatkov had a sort of influential paper where they showed that essentially by cross-referencing this anonymized data set with the IMDb data set, you could reattach a significant fraction of the records here, the anonymized records with people's names. Okay, there was again a class action lawsuit. It turns out that thanks to the attempted Supreme Court confirmation of work, there's a special law protecting the privacy of video rental records, and it was settled for an undisclosed sum, and the second Netflix challenge was canceled. Okay, and finally, I think this is one of the most interesting examples. It's sort of clear that, maybe from the last two examples, that like removing people's names isn't a sufficient privacy protection. But you might naturally think that releasing only like aggregate information rather than information about individual data records, maybe that's it. Okay, so we've all got DNA, which is sort of a really long string of data. Okay, in every entry, we could have one of 4 base pairs. And in most positions, you and I have the same base pair as each other because we're both human beings. Okay, but there are certain positions called single nucleotide polymorphisms where my DNA might differ from yours. There's some amount of variation in the population. So in something that's called a genome-wide association study, what you might try to do is gather a collection of people who share some phenotypic trait, like they've got some disease, and in an attempt to learn what kinds of sort of genotypic correlations to that trait, you might just compute a bunch of average statistics. For each of these sort of genome positions corresponding to the single nucleotide polymorphisms, you might compute what fraction of the people in your population have each base pair. Okay. And so these are sort of useful medical data sets, and they seem pretty innocuous, right? Every entry in the data set is just an average over, say, 1,000 people. Okay, like a fraction. What fraction of people have an A here? Okay. So these kinds of data sets were released. But in another influential paper by Homer et al., it was sort of observed, and there's been lots of subsequent work explaining why this is, that even though maybe each of these individual averages is innocuous on its own, because there's millions of them, if I know your genome, I can actually reliably determine whether you were in the study or not, whether you were in the sort of batch of 1,000 people used to compute these statistics or not. And that's a dangerous thing for me to know, because if, for example, everybody in this set has some disease, learning that you were in the study reveals that you have the disease. Okay, so when this was pointed out, the National Human Genome Research Institute they removed these data sets from the public domain. Okay, so when you don't think carefully about protecting privacy, and you just try sort of ad hoc protections, bad things can happen. So what this talk is about is how you might think carefully and precisely about what it means to protect privacy and how you might do it. But I want to reflect for a moment about the question, like, what is privacy? Okay, from these examples, we've learned maybe a couple of things that privacy is not. Okay, so you don't obtain privacy just by sort of redacting information that seems personally identifiable, things like name and zip code. And you also don't protect privacy just by releasing aggregate statistics. Like, it's tempting to think that aggregates are protective, but the DWAS example shows that they're not. Okay, so let's think about what we might mean when we say privacy. Okay, and maybe here's a first attempt. Okay, maybe privacy, whatever that is about promising people freedom from harm. Okay, so maybe we can try to formalize the following kind of idea. Okay, an analysis of a data set is private if I can promise that the data analyst knows no more about some participant, Alice, after the analysis than he knew about Alice before he ran the analysis. So yeah, maybe that would be something we can achieve. It sounds pretty good. So that's an extremely strong guarantee. The problem is it's essentially impossible to achieve if you want to be able to do anything at all with the data. And here's the sort of a cartoon example to explain why. Okay, suppose an insurance company happens to know that Alice is a smoker. Okay, whether you're a smoker or not is sort of publicly observable. And suppose that I run an analysis that discovers some fact about the world. Okay, that smoking and lung cancer are correlated. Okay? Well, this might cause the insurance company to raise her rates. This actually used to be sort of the go-to example in the differential privacy literature before the Affordable Care Act was passed, and I was quite worried I would have to change my slides now that pre-existing conditions can't be used to discriminate insurance rates, but I think I'm going to keep the slide for now. So the question was her privacy violated? Right? If I learn this fact about the world, that smoking and lung cancer are correlated, and an insurance company knows that Alice is a smoker, she might have come to quantifiable harm in the form of her insurance rates rising. Okay? But, okay, so you could perhaps take the position that her privacy was violated, but that's not what I want to do for two reasons. First, if this kind of thing is a privacy violation, then you just can't use data at all. You can't do science subject to privacy protections because learning facts about the world, correlations that exist in the underlying data, that's what we wanted to do with the data, right? You could repeat this example with any correlation you learned about the underlying data. But maybe more fundamentally, the thing that I learned here, although it caused Alice to come to harm, was not a fact specific to Alice. It was a fact about the world. It was a fact that I could learn even without Alice's data, right? That smoking and lung cancer were correlated. So although this was some fact about the world that once it became known caused Alice to come to harm, it wasn't Alice's secret to keep. It wasn't something that was a function of her data. Okay, and so differential privacy, which I'll tell you about in a moment, takes the position that this kind of thing is not a privacy violation. Okay, so let's amend our definition. Let's give a second attempt. Okay, let's say that an analysis of a data set is private if the data analyst knows almost no more about Alice after the analysis is complete compared to what he would have known had he conducted exactly the same analysis on an identical data set that happened to have Alice's data removed. Okay, so rather than comparing the state of the world after the analysis has been done to before the analysis has been done, what I want to do is compare the state of the world after the analysis has been done with Alice's data compared to what it would have been had the same analysis been done without Alice's data. Okay, this means, if this is the case, that although Alice might come to some harm as a result of the study, it wasn't because of the use of her data. Okay? And anything you were worried about happening to Alice would have happened anyway had her data not been a part of the data set. Okay. And this is the kind of thing we're going to try to formalize with differential privacy. So it's maybe a quick show of hands. Who here has heard the words differential privacy before? And who here thinks they could repeat the definition if need be? Okay. So a bunch of people have heard about it, not everyone. If you guys have been following the academic literature, maybe you've heard about differential privacy for a while. When I give this talk to sort of a more industry audience, at this point most of them have heard about differential privacy as well, but basically only since October when Apple announced that they were going to include differential privacy protections in their data gathering in iOS 10. So if you look at the Google search trends for the phrase differential privacy, you can guess when the Apple mobile developers conference was. But here's differential privacy. And by the way, Cynthia Dwork, Frank McCherry, Kobe Nissim, and Adam Smith just won the Girdle Prize for this paper a couple of weeks ago, so if you run into them, buy them a beer. Differential privacy is a property that a randomized algorithm might or might not have. Okay, it's a property of a randomized algorithm. A randomized algorithm is going to take as input some data set. Okay, it's going to perform some computations, flip some coins, and then it will output something. And because it's a randomized algorithm, its output will follow some probability distribution. What differential privacy requires is that when I look at the distribution of outcomes induced by the algorithm when I plug in some data set D. And then I look at the distribution on outcomes induced by the algorithm when I plug in a data set that has one person's data removed or changed. So these two distributions should be quantifiably similar. Okay, a little more formally, if I've got a data universe X, this is sort of the space in which rows in my data set can live. Okay, I'll say that two data sets are neighbors if they differ in the data of a single individual. Okay, so think about D as being the data set including your data, and D prime as being the data set that's had your data record removed or modified in an arbitrary way. Then what differential privacy requires, and there's a privacy parameter epsilon, is that for all pairs of neighboring data sets, D with your data and D prime without your data, and for any event X in the outcome range, the probability that the event occurs if the algorithm is run on your data is almost the same as the probability that the event occurs if the algorithm is run absent your data. We're almost the same in a 1 plus epsilon multiplicative factor. So this is the definition. I'm gonna sort of explain in a moment a little bit about what it means. Okay, but let me first observe that it's got an extremely useful property. Okay, which we'll call post-processing. Differential privacy is robust to post-processing. Okay, so what that means is if I've got some epsilon differentially private algorithm, and I've got any other function f that I don't need to know anything about f, then if I run my epsilon differentially private algorithm and I post-process the output with f, I haven't made the result any less private. Okay, the composition of these two functions is still epsilon differentially private. Okay, so by thinking about the outcome of a mechanism, I cannot make it less private, no matter how I think about it. Okay, so going back to the definition, you can think about f as being a function that takes as input, in particular, the outcome of your analysis x, but also anything else about the world that's relevant, whether a butterfly has flapped its wings in Brazil, any other input about the world that's relevant, and maps these aggregate sort of inputs to some event about the world that you care about. Okay, so when I say that differential privacy is promising that any event that any event in the range of the algorithm is almost no more likely to occur if your data is in the data set compared to if it's not, you can literally take that to be any event that you are worried about. So X could literally be the event that you are re-identified, or X could be the event that you are denied an insurance claim, or X could be the event that you receive annoying phone calls during dinner. Okay, so differential privacy is literally claiming that for all of these events, for any event that you might care about, the probability that that event occurs is almost the same whether or not you allow the analysis to use your data or do not. Okay, so sort of a utilitarian definition of privacy. You have very little incentive to restrict your data, okay, because you might as well allow the analysis to use your data. No event that you're worried about is going to become substantially more likely. Okay. Differential privacy has another nice property in that it's this privacy parameter epsilon degrades gracefully when you run a bunch of differentially private algorithms over and over again. Okay, so if I have k algorithms that are all epsilon differentially private, like I've got k differentially private subroutines, and I run all of them, then in aggregate, the algorithm I have is k times epsilon differentially private. Okay, and I can remember post-process these results as well. Okay, so what these two things mean together, the robustness to post-processing and the composition properties, is that differential privacy is compositional in an extremely useful way. Okay, just as you do in regular algorithm design, you can keep track. You can build up a library of differentially private subroutines. Okay, and so long as you access the data only via these differentially private subroutines, you can combine them in any way that you like, and have an easy way to keep track of the total privacy cost of the algorithm. And in this way, you can think about a privacy budget as a resource that you expend as you access the data. Okay, so what this means is that private algorithm design, like regular algorithm design, can be modular. Okay, even though differential privacy might be a relatively complicated property to prove from first principles about a sophisticated algorithm, generally you don't have to prove it from first principles. You have privacy guarantees about simple algorithms, and then the privacy guarantees for complicated algorithms arise from these simple compositional rules. Oh. So we've seen the definition, and we've seen that if I have a couple of differentially private subroutines, I can glue them together, and the privacy guarantees sort of fall out from these simple rules. Why don't we think about a couple of simple things that we might be able to do with differential privacy? Let's try to build up a couple of these simplest subroutines. Okay, and then once we've got a couple, we can try to glue them together into a more sophisticated algorithm. So probably the simplest thing you could do on a data set is to compute a sum or an average, to answer some kind of numeric value query. Okay. So what turns out to be a relevant property for a numeric value query for differential privacy is what I'll call its sensitivity, which basically just is measuring the effect that a single individual's data can have on the result of the answer to that query. Okay, so we'll say that a function f, which outputs a numeric value, has sensitivity c if, for any data set d, when I compute the value of this function on d, and then I change one person's data, and I get a data set d prime, and I compute the value of the function on d prime, the value of the function hasn't changed by more than c. Yes, that's all it means that a function has sensitivity c. So for example, the question, how many professors are in this building, that has sensitivity 1. Right? If I add or remove one person from this building and can't change the answer to this question by more than 1, if I ask what fraction of people in this building are professors, that has sensitivity only 1 in n, where n is the number of people in the building. So it turns out that answering numeric value queries subject to differential privacy is extremely easy. Here's something called the Laplace mechanism, but it's a really simple thing. You just compute the answer exactly, and then you perturb that answer a little bit with some mean zero noise drawn from the Laplace distribution, with standard deviation that's scaled just to the sensitivity of the query divided by epsilon, the privacy parameter you want. Okay. So it's not hard to show that this is epsilon differentially private, and it gives pretty accurate answers. So I probably underestimated the number of people in this building. It turns out to be a pretty big hotel, but I guessed maybe there'd be 500. If there were 500 people in the building, the fraction of the question, what fraction of the people in the building are professors, would be answered to accuracy 0.2 or up to error 0.2%. Okay, so small error. So that's one simple thing we can do. Of course, not everything we want to do is answering a numeric value query. Right? For example, I might want to know what is the modal eye color in the building. Eye color is like a categorical thing. It's not like I can't add noise to blue. That doesn't make sense. Okay, but nevertheless, this is the kind of question that's easy to answer with differential privacy guarantees. Okay. What you want to do is you want to specify a function that you think tells you how good each answer is for your data set. So for example, for the eye color question, I might say that, the quality of the answer red, given my data set, is equal to the fraction of people in the building who have red eyes. Okay, and so asking what's the modal eye color is asking for the color that has the highest quality score according to this measure. And now we're in a world with sort of numbers. And so there's something called the exponential mechanism, which is again a very simple thing to do. You just randomly output a color, randomly choose an element from your range, biasing it towards things with high quality exponentially. Okay, so I'm going to output a color with probability exponentially proportional to its quality. Okay. This is epsilon differentially private as well, and also accurate. So again, if there were, under the assumption that there's 500 people in this hotel, you can find a color whose frequency is within 0.5% of the modal eye color in the hotel. Okay. So, so those are two, like extremely simple primitives. Let's just think very briefly about how we could glue them together to do something a little bit more complicated. Okay. So let me think about sort of a very general formulation of a machine learning problem called empirical risk minimization. Okay. You've got some data set with n data points, and your job is to find, to train a model, basically, to find a parameter vector of data that's going to minimize some loss function with respect to your data set. So this model's essentially all of supervised learning, from things as simple as linear regression, where you're just trying to find a vector of sort of linear coefficients to minimize your mean squared error, all the way up to sort of deep learning, where you're finding a billion parameters to minimize the loss of a neural network. Okay. So this is a general problem. The way it's typically solved in practice is via stochastic gradient descent, which is an extremely simple algorithm. You've got your initial parameter vector set to be something, and then for some number of rounds, all I'm going to do is I'm going to pick a data point at random. Okay. I'm going to compute the gradient of my loss function with respect to that data point. And I'm going to take a step away from the gradient to get my new parameter vector. Okay, so I'll just update my parameter vector by stepping a little bit away from the gradient. Okay, this works great. This is, how people do lots of modern machine learning. And the reason this works, if you want to prove, for example, convergence theorems, the reason this works is because at each round, when I look at the expected value of the gradient I found at each round, the gradient computed on a random one of my data points, in expectation, this is equal to the true gradient of my loss function at my parameter vector. Okay, so stepping in a direction away from the gradient is what I want to do to minimize the loss. Okay, well, can we make something like this private? Well, I think it's extremely easy. Every coordinate of a gradient is just a numeric valued query on the data set. That's something that we know how to answer privately with the Laplace mechanism. Okay, so one simple thing we can do is we can just perturb every coordinate of every gradient at each round of the computation with appropriately scaled Laplace nodes. Okay? The accuracy analysis still goes through. It's a little bit, the accuracy analysis is a little bit complicated, but the basic reason why it works is just because this fact that we relied on before, that the expected value of the gradient, or the expected value of our estimate of the gradient was unbiased, was equal to our gradient, that's still true, because we're just adding sort of mean zero noise to this thing. And, okay, so you'd have to do a little bit of work to analyze the accuracy of this thing. Of course, you could just run it and see how well it does. But the privacy analysis is extremely simple and compositional. Okay? It follows from the fact that, number one, the Laplace mechanism is differentially private. The only time we're actually ever touching the data is when we estimate these gradients. Okay, and we do that via the Laplace mechanism, perturbing every coordinate. So each of those steps is differentially private. Post-processing doesn't degrade privacy. So, I perturb each coordinate of the gradient with the Laplace mechanism, and I update my parameter vector, but that's just post-processing. That doesn't degrade privacy. And finally, privacy guarantees compose. So, for each of these t steps, I have some privacy cost, and the total cost of the algorithm is just the sum of the costs of each of those t steps. Okay, so because privacy is compositional, even for sort of a reasonably complicated algorithm that you can use to train neural nets, the privacy analysis goes through without having to, complicated algorithm. And at this point, there's more than a decade of research thinking about other things you can do with these guarantees, and it's a lot. Essentially, any data analysis task where what you're trying to do is learn statistical regularities about the data rather than facts about individuals in the data can be done subject to differential privacy. There's a big literature on this. So basically, you can do machine learning subject to differential privacy. It's great. What I want to do in the second half of the talk is just point out that differential privacy turns out to have some nice properties that we've discovered in the last few years that basically show that, well, one way to think about it is, in some sense, machine learning is the only thing you can do subject to differential privacy. But another way, the tools of differential privacy give you a useful robustness guarantee about your data analysis, even if you didn't care about privacy initially. Okay. Sort of said at a high level, with a lot of details missing that I'll fill in a moment. Epsilon differentially private algorithms cannot overfit data sets by more than epsilon. Okay, when you're doing machine learning, one thing that you're always worried about is overfitting. Like, what you want to do is discover true facts about the world, but you only have access to some finite data set, and you're worried that when you do your analysis, you're not discovering facts that generalize to the world, but facts that are specific to the irregularities of your data sets, that you're fitting the noise. Okay. People go to sort of great lengths to try to avoid this, but the claim is if you're doing your analysis subject to differential privacy, you don't have to, in that it is always the case that anything you discover about your data set will generalize automatically to the distribution of the data set. So let me, to try to fill in some details to this informal claim, let me sort of specify the details to a simple model. Okay. So again, we're going to have our data universe X. This is sort of just the space in which rows of a data set can lie. Okay. And we've got some distribution. Think about this as sort of the thing we want to learn about, our model of the world. Okay, we want to learn facts about the distribution, is smoking correlated with lung cancer? But we don't have direct access to that. We just have some finite collection of records, right? We've got the 1,000 people who walked into our hospital and agreed to share their records with us. So rather than being able to directly ask facts about the world, our only access to the world is through a data set, which I'll assume consists of some endpoints that are sampled from the distribution. Okay, so our goal is to take this data set and use it to learn about the world. And just to keep things simple, let's say that the kinds of things I want to learn about the world can be specified as what I'll call statistical queries, which are just predicates, that take as input one person's data and say, give me a number that's either 0 or 1. This person satisfies some property or they don't. They are a smoker or they're not. Okay, so if I've got a statistical query, the true answer, the thing that I want to learn, the value of that query, is just the expected value of that query on the distribution. How many people in the world, or what fraction of people in the world, are both smokers and have lung cancer? Okay, but I can't directly evaluate that. What I get to do is I get to design a statistical estimator that will, as a function of my data set, attempt to answer these queries. So I'll give the query to the algorithm, it'll do something, I compute the empirical average, and it'll tell me some number which purports to be the answer to this query. Okay, so this is a simple formalism. Everything I'm going to say extends beyond it, but let me just point out that even with these simple classes of queries, I haven't lost a lot of generality. In particular, of course I can ask for simple facts about the data sets, like means, variances, correlations, things like that. But if I've got some arbitrary model and I want to estimate its predictive accuracy, it doesn't matter what the model looks like. The question, what is the mean squared error of this model? What's the 0-1 loss of this SVM or this neural network? That's always a statistical query of this sort. And we just looked at gradient descent. The gradients of a loss function that you're trying to train, those are also queries of this sort. And so for basically any machine learning task, not only can you evaluate its quality in this model, you can train it. So this is a reasonably expressive formalism. Okay, and what I want to think about are adaptively chosen queries, by which I mean the following. Suppose I've got some arbitrary data analyst, okay, possibly malicious or possibly just naive, who wants to ask a sequence of queries to the data set, each one of which might depend on the answers he's gotten previously. Okay. So we've got our data set here, drawn IID from some distribution, and we've designed our statistical estimator. So the data analyst will ask his first query and then get his first answer. As a function of that, he'll ask another query and he'll get another answer. Okay, so on and so forth. We'll ask k queries and all. Okay. The way I want to evaluate the quality of a statistical estimator is by, basically just equipping it with confidence intervals. Okay, I want to say that a statistical estimator is epsilon delta accurate for a sequence of k queries if no matter what the data analyst is, and no matter how the data analyst is behaving, and no matter what the underlying distribution is, I've got sort of simultaneous coverage with confidence intervals around all of my answers. So with probably 1 minus delta, for every question the analyst asked, the answer provided was within epsilon of the true answer. With confidence intervals. So how well should we expect to be able to answer queries of this sort? And a good baseline is sort of the non-adaptive case where the data analyst asks all of his queries up front. Okay. In this case, it's sort of there's a really obvious thing to do. Like, how should you estimate these answers, which are like, what's the average value of this question on the distribution? Just answer with the empirical average. The empirical average is an unbiased estimator of the truth in this case. Okay. And it's not too hard to see that if you want 1% error 99% of the time, just answering with the empirical average will allow you to do that for exponentially many queries, for really a lot of queries. Unfortunately, it turns out that these guarantees entirely break down in the common case in which the questions are asked adaptively as a function of the previous answers. Okay, intuitively because if the question I'm asking today is actually a function of the data set, then the data set is no longer an unbiased estimate for the truth. Okay, and sort of naive learning approaches will quickly overfit to your data if you are making repeated use of it. If you're reusing your holdout set and not gathering a fresh holdout set every time you want to train a new model. Okay, so rather than being able to answer exponentially many queries in the sort of textbook statistical setting where all of the analyses you want to run are chosen independently of the data, when you're in the common case where the analyses you want to run are actually suggested by the data, it turns out you cannot guarantee that you can answer more than linearly many queries. So simply answering with the empirical average is exponentially worse. Okay, so that doesn't mean that it's necessarily impossible to answer queries in this setting. It just means that answering in the sort of obvious way with the empirical average, that's a bad idea. Okay. But it turns out differentially private algorithms don't have this problem. Okay, so here's a theorem. Don't worry about the exact parameters. I'll tell you what it means. Here's a theorem we proved a couple of years ago. So if the way you're answering the queries has two properties. Number one, it's differentially private. And number two, it gives you answers that are accurate with respect to the sample. It gives you answers that are close to the empirical answers on your data set. Then you automatically know that the algorithm hasn't overfit to your data set and that those answers are accurate with respect to the underlying distribution. Okay. Okay? And it's important that you have both of these properties, right? The mechanism that just answers with empirical averages, that's perfectly accurate with respect to the sample by definition, but it's not differentially private, and we see that that's completely broken. And I could ignore the data set. I could just give random answers to every query you ask. That'll be perfectly differentially private, but won't be accurate with respect to the sample. Neither of those mechanisms are going to be good for sort of learning the truth about the distribution. But if you manage to have both of those properties simultaneously, then the theorem is you cannot overfit. Anything you learn about the data set, you're guaranteed to be true about the underlying distribution. Okay, so we immediately get some consequences of this theorem. Okay, an extremely simple modification of the empirical of the estimator, which simply answers with empirical averages, already gets a pretty big quantitative improvement. If every time you ask me a query, I don't just tell you the empirical average, but I tell you the empirical average perturbed with a little bit of Gaussian noise. This is something that maybe seems a little unnatural. Like if I want to get higher accuracy, perturbing things with noise seems like I'm moving in the wrong direction. I'm degrading the answer, it seems. But because it prevents overfitting, it turns out that just perturbing the empirical average with noise allows you to answer quadratically more queries with valid confidence intervals around their answers than if you didn't add the noise. Okay, so this is the case where adding noise for differential privacy, although you get privacy as a side effect, also has the property of dramatically increasing the accuracy of your answers. Not the accuracy with respect to the sample, which of course is always degraded when you add noise, but the accuracy with respect to the distribution, the thing you really wanted to learn about. Okay. It's a little bit counterintuitive, but the reason is by slightly degrading the accuracy that you get with respect to the sample, you're dramatically diminishing the ability of your analysis to overfit the sample, which is a different source of inaccuracy. Okay. There's more complicated things you can do. We've been studying how to privately answer questions on data sets for a decade. So if you take sort of the state-of-the-art mechanisms from this literature, which do things that are more complicated than just adding Gaussian noise, it turns out that as long as your data set is bigger than the dimension of the data, then rather than just being able to answer quadratically many queries, you can answer exponentially many queries. Okay, this is approaching the sort of guarantees that you had in the non-adaptive setting. So you can almost entirely eliminate the sort of cost that adaptivity has of being able to do some degree of data dredging on your ability to confidently avoid overfitting. Okay, and let me just leave you with one more practical example of something you can do. Okay, so a typical setup in data analysis is I'm going to divide my data set into a training set and a holdout set. Okay, and I'll do whatever I want on my training set, but then I'll use my validation set, my holdout set, to check that I haven't overfit, to validate my results. Okay, the problem is, if you actually want that to work, you're only supposed to use the validation set once, right? Otherwise, you need a new one. But that's not what people do, because data is valuable. So, if I try something and I don't like the results of my validation set, typically I'll go back, I'll tune my parameters differently, I'll train a new model, and I'll iterate, I'll check on my validation set again, and that will, cause you to oftentimes overfit the holdout set. So here's a method we developed using differential privacy to allow you to sort of perform data analysis in the way that you're already doing it, by sort of reusing the holdout set over and over again many times adaptively, while still allowing this to, still giving you validity guarantees for the analysis. It's an extremely simple algorithm. Here's the Python code for it. So don't bother reading the code, I'll just tell you what it does. Every time you want to ask a query to the holdout set, what is the error of my model? What this algorithm will do is it'll compute two numbers. It'll compute the error of your model on the training set, and it'll compute the error of your model on the holdout set. And it'll do a noisy comparison to see whether these two numbers are close or not. Okay. If these two numbers are close, if the error of your model is close on the training set and on the holdout set, then it won't like waste information about the holdout set. It'll just give you the answer on the training set. And that's going to be okay because that event only happens when the error on the training set is close to the error on the holdout set. On the other hand, if it happens that you overfit the holdout set, meaning the error on the holdout set is, say, substantially larger than the error on the training set, it will point this out to you. It'll give you the answer on the holdout set, but subject to differential privacy. It'll add some Gaussian noise. Okay, so it's answering queries in a way that, number one, always keeps the holdout set differentially private, but number two, doesn't waste accesses to the holdout set. It doesn't touch the holdout set when you haven't actually overfit the training set. So there's a theorem associated with this, but let me instead take you through a simple empirical evaluation. Suppose I've got some data set with maybe 20,000 people in it, and let's say 10,000 features. Okay, so 10,000 features, one for each person, and let's say it's a Boolean data set, so every person, the thing I'm trying to predict is a class label for every person. Do they have lung cancer or not? Is it 1 or -1? Okay, and I'm going to perform a reasonably natural statistical procedure called stepwise variable selection, and using the holdout method. So I'll split my data into training set and a holdout set, and then what I'm going to do is I'm going to try to find the best k variables on my training set, by which I mean the k variables that are most correlated with the label. And in an attempt to avoid overfitting, whenever I find on my training set that a variable is correlated with the true label, I'm going to check that on the holdout set. Okay, and I'm only going to actually use those variables that are correlated with the label both on the training set and on the holdout set. Okay. So I'll get some set of k variables correlated with the labels. I'm going to then train a linear model on those k variables and see how well it does. Okay, and while I'm at it, I might try to find the best value of k. Okay, so suppose I'm doing this, and in fact, there's no correlation to be found. The data is entirely random. The features are just drawn from a Gaussian, and the labels are actually independent of the features. So there's, I have no hope of achieving any non-trivial prediction here. And let's see what happens if I run this analysis using a standard holdout and using the differentially private holdout. Okay. Well, so there's 3 lines on each of these plots. The blue line is the training error. The green line is the estimate of the error on the holdout set. And the red line is the true error of each model. And in this case, there's no non-trivial model, so the true error is always 50%. Okay. So in both plots, of course, we overfit the training set. There's no protections for the training set. But using a standard holdout naively, what you find is that there's no way to detect this overfitting, because when I check what my error is on the holdout set, that looks non-trivial, even though it can't be on this data set. Okay, and so you actually overfit the holdout set as well. But when you use the differentially private holdout method, you still overfit the training set, but you can detect that, because when you try to evaluate your error on the holdout set, it gives you the right answer. Okay, so in this case, we can correctly detect overfitting. Now, of course, that guarantee wouldn't be super useful if I couldn't detect signal when it existed. So let's just see a simple example where there is something to detect. Okay, so suppose we repeat the experiment, but now out of these 10,000 attributes, 20 of them really are highly correlated with the label. So there really is a linear model to learn here. Well, when you look at the sort of standard holdout reuse, what you find is that if I tried to pick the best model by checking my results on my holdout set, it would look like the best thing I could do is, add lots and lots of features. Because again, I'm overfitting the holdout set. The holdout error is not tracking the true error. But when I use the differentially private holdout, as the theorem guarantees, the holdout error tracks the true error, and we're able to correctly detect the model size. Okay. So, to sort of summarize, differential privacy is a definition, but also at this point a sort of a collection of tools that gives you a rigorous, provable guarantee of privacy in the sense with a strong privacy semantics, right? Like you're able to sort of explicitly say what the guarantee means. That no matter what it is you're afraid of, it's almost no more likely to occur if your data is in the data set compared to if it's not. And it's not so hard to achieve because you have a simple set of subroutines that are easy to show are differentially private, and more importantly, composition theorems that allow you to combine these in sort of arbitrary modular ways to design complicated algorithms without having to redo the privacy analysis from scratch. You can do this with relatively little expertise, and in fact, colleagues of mine at Penn are developing ways to automate this analysis, programming languages that, by virtue of the fact that they compile, must be differentially private. The reason these are possible is because of the modular flavor of the analysis. And this toolkit turns out to be useful even when privacy wasn't the thing you were worried about to start with. Okay, like one objection to differential privacy is often that, okay, we all want privacy, but adding noise to our results, that's not acceptable because, we want the exact results. We don't want to tolerate error or approximation. But it turns out that differential privacy can actually cause your analyses to be more accurate, not less accurate, when what you really want to learn about is the world, the distribution from which the data was drawn, rather than your particular data set. Because differential privacy provably detects overfitting and gives you a useful tool kit that helps with learning, even when privacy wasn't the first order concern. Okay, so that's all I've got. But if you want to learn more, we've got a textbook that's joint with Cynthia Dwarf that's available as a PDF for free. This is a good way to sort of get into the field. It's a collection of papers detailing this connection between privacy and overfitting. And thank you very much.